IUAC, which is earlier which was known as your Nuclear Science Center, New Delhi, from 1998 to 2000. In January 2001, he was awarded Young Scientist Project under Department of Science and Technology, Government of India. And after that, he joined Institute of Physics, Bhubaneswar, a research institute under the Atomic Energy, Department of Atomic Energy, in August 2001 as senior lecturer and become a full professor there in June 2016. He has published lot many papers and 150 papers are in his credit, which are international. He has also written books, and the name of the book is Nanofabrication by Ion Beam Sputtering, Fundamental and Application. He has also been the guest editor of a special issue in Applied Surface Science and Nuclear Instrument and Methods in Physics Research, Section B. He is an executive body member of Ion Beam Society of India, type member of the Indian Physics Association, Plasma Science Society of India, and Electron Microscopy Society of India. He is an international scientific committee member of biennial international workshop on nanopatterning. He was the chair for international conference on ion beam induced nanostructuring of materials, IINM 2011 in 2011, and a local organizing committee member of several conferences like 18th International Conference on Ion Beam Analysis, IBA 18 2007, 20th International Conference on Atomic Collision in Solids, ICACS 20, International Conference on Physics at Surface and Interface, PSI, in 2004 and 2014, and 39th meeting of Electron Microscope Society of India, scheduled in July 2018. In this talk, Professor T. Som would like to share some glimpse of IBA, your ion beam analysis. Basically, ion beam analysis is a very important and powerful characterization tool of materials. For instance, one can study thickness, measurement, compositional analysis, defect engineering, and so on. There are various or there are several ion beam analysis techniques which uses energetic ion beams, which is secondary ion mass spectrometry, Rutherford backscattering, elastic recoil detection analysis, nuclear reaction analysis, channeling, etc. IBA has found use in number of variable applications ranging from biomedical usage to studying your ancient artifacts. Finally, I am sure you all will enjoy the talk. And now I will pass over this webinar on the finger of Professor T. Som. Over to Professor T. Som. Sir, please.
Thank you, Dr. Roy. Thank you, Dr. Kataria, for inviting me and so nice introduction. It's always it has been a pleasure to work together. Worked a lot with Yaspal also when he was a very young PhD student. Thank you, Yaspalji. So let me start. I will request Yaspal to now move to the next slide. Okay, this is a brief outline. So I'll first show based on the low energy accelerators, what are the places right on today, basically these ion beam analysis, mostly RBS and RBS is nothing but a short form of Rutherford backscattering spectrometry. In 1911, Lord Rutherford had discovered this, and it's probably is being taught to us from undergraduate days itself. And then few applications of RBS, and then there's a very special format of Rutherford backscattering spectrometry technique, which is known as ion channeling technique, which is applicable only for single crystalline materials, rather analysis of single crystalline materials or epitaxial thin films. And then I'll briefly touch upon elastic recoil detection analysis in short, which is known as ERDA. It's basically to detect hydrogen and its isotopes, which are otherwise difficult to be probed by most of the analysis techniques because of its lightest possible mass. And finally, I will conclude. Yes, Padji, please. Well, these are the three most prominent laboratories where RBS is regularly being done. IIT Kanpur machine is for the time being down. Likewise, Guru Ghasidas in Vishwavidhyalaya machine is right now probably undergoing some maintenance. So I'm not including those facilities. In principle, they can do as well. No second thought. And but these are the places where routinely it is being done. Next slide, please. Well, as has been told that by Dr. Roy in his introduction, as there are several ion beam analysis techniques which are being employed to study different class of materials, to study different elements. What they do is basically the ion beam analysis techniques are employed to for analysis of materials, basically elemental analysis. And we know composition analysis is a very important aspect of day-to-day life. And particularly, there are several techniques which are unique. And unique in the sense, if we don't apply these ion beam analysis techniques, then probably some such studies cannot be done in it. And well, the most popular one is secondary ion mass spectrometry, particularly again. When I say most popular, I would also add that it is popular for semiconducting materials analysis. And it's extremely sensitive, but it's destructive as well. So there is a trade-off. So what we want, but it's very sensitive to elements like hydrogen to uranium, basically all the elements in the periodic table. It can detect with high detection limit. And basically the range is pretty high. What I mean is parts per billion to parts per million it can go. And depth resolution is also pretty high, 5 to 20 nanometer. So basically, kind of dopant analysis, the depth distribution in semiconductor industry, optoelectronic industry, SIMS is almost a mandatory kind of technique. However, this is a non-destructive technique, I repeat it. Now, let us see the other ion beam analysis techniques, few of which I will talk about, like ERA and RBS. These are rather considered to be non-destructive techniques. And Rutherford backscattering spectrometry, for instance, it is typically for low energy ions. So when you talk about, basically, it can be probed by both hydrogen or helium ions. Okay, and sometimes they are called as hydrogen-induced backscattering spectrometric studies are known as Higgs, like or proton-induced backscattering spectrometry as well. And sometimes this helium-induced RBS is popularly known as alpha spectrometry, kind of that. So here you can see that J, that is atomic number, depends, rather decides that what kind of sensitivity one can expect or what kind of detection limit one can visualize in reality. For instance, if you see any light element, if we talk about for detection using RBS technique, you can see that 1 to 10 atom percent is the detection limit. If we go below that, it will be difficult to detect. And now, as Z tends towards 20, even a lower atom percent presence is okay. Like 1%, 1 atom percent would be rather valid for kind of Z value around 1920, whether 10 atom percent will be needed to detect if Z value is approaching towards 4, 5, like that. And then higher is the Z value, you can clearly see that you can go down much more. Okay, and for Z greater than 70, even 0.001 atom percent presence is also absolutely a reality. And here also depth resolution can be 2 to 20 nanometer. There are specific techniques known as high resolution RBS technique, where very different ion optics, etc., are used, and they can go down to even lower sensitivity and depth resolution. Now, I'll talk about conventional RBS technique today. Nuclear reaction analysis is another technique, very useful, non-destructive again, where several new nuclear reactions are being used. We all are aware of such nuclear reactions in nuclear physics. And some preferable nuclear reactions are picked up, and they are used as an advantage to detect light elements. Mostly are the elements which are not so sensitive to be detected by RBS, like hydrogen, beryllium, boron, carbon, oxygen, fluorine, etc. Here depth resolution deteriorates. Its typical value is around 15 to 30 nanometer, and a few hundreds of ppm will be quite okay. And then elastic recoil detection analysis is a very dedicated technique, again using low energy ion beams as a projectile ion. They're used to detect recoiled hydrogen atoms and its isotopes. So basically, which is otherwise extremely difficult to quantify in an absolute fashion, that is being possible to be done by employing elastic recoil detection analysis techniques where hydrogen, deuterium, tritium, everything, if they are present together in a material, that can be detected in a non-destructive way with reasonably good sensitivity and high detection limit. Okay, so however, this is not limited to only hydrogen, deuterium, or tritium. If we use higher energy ions and other higher projectile masses, then any element below that projectile mass can be detected in principle using elastic recoil detection analysis. Now, why I am stressing that this is the scenario that you see on your screen, that recoil ions of hydrogen, deuterium, and tritium, that means hydrogen and its isotopes are possible to be detected. That is because this is the case where, like RBS using low energy ions, ERDA using low energy ions will be meaning only helium ion is the projectile. And you can imagine, so the RBAs for Rutherford backscattering spectrometry, there is a difference with ERDA. The basic difference is, as you can see, here the forward recoil of the recoiled particles which get scattered in the forward direction, or the particles which are recoiled in the forward direction. That means the scattering recoil angle is less than 90 degrees. Those are the particles which can be detected. And in Rutherford backscattering spectrometry, the particles which get backscattered, that means projectile ions are helium. And that helium ion itself gets backscattered, and those backscattered helium ions are detected using a detector. And so that has to be in the backward direction. That means anything higher than 90 degrees to 180 degrees. And you can imagine 180 degree will be a little bit difficult ball game, because ions are also penetrating or coming on from the same direction. So with that brief interaction, I can probably tell you that what all important aspects that one can study by using RBS technique. Very importantly, as I told, composition analysis is at the topmost agenda. And one can do a lot of thin film analysis, which is actually very important for almost every sphere of materials research and many areas of electronics, electrical engineering, electronics engineering, of course in physics, and energy research and everything. Uh, and then impurity content. Let us not forget the entire device industry is banking upon multiple ion beam related processing steps, and a lot of dopant atoms need to be implanted, and those are considered impurity atoms after all in the host material. So the detection of impurity content and then diffusion study, homo or heteroepitaxy, analysis of hydrogen and isotopes is also possible. Of course, not by RBS. We have to just take help of PRD, but just to you can ignore that line right here. We can go to the next slide. So you see, this is a very kind of sketch to schematically give you a feel that what is being done during RBS study. I mean, geometric aspect of RBS study you can see on the screen. We have identified incident ion with mass M1 and its atomic Z1, and it is falling. If it falls on a traveling material having mass M2 and atomic number Z2, M1 has to be less than M2. If M1 becomes greater than M2, then we cannot consider RBS anymore. We have to take help of RDA measurements. So this is the fundamental thing. A small mass is going to heat bigger mass, and automatically just to go back. And these backscattered particles, basically these M1 particles, they come back, they become energetic, or they remain energetic, and they come back and get detected by a suitable detector. And this is what is, in principle, formalism of Rutherford backscattering spectrometry. And this has four important aspects. One is the kinematic factor, and another is scattering cross section, and then energy loss. Okay, uh, and couple of other important things like solid angle, and then etc., which one need to take care of. And you can see that kinematic factor decides that with which energy the backscattered particles will come back to the detector. Scattering cross-section is, of course, the probability of happening this backscattering phenomenon for a given target projectile combination with a given ion energy. And you can see very clearly that this depends, the scattering cross-section depends on the inverse square of ion energy. So higher is the ion energy, okay? So cross-section will be lower and lower. And then it also is dependent on this backscattering angle by inverse to the power 4, sine theta inverse to the power 4. So fourth power of sine theta, okay? So it depends, a lot depends on what is the backscattering angle where the detector has been set. And it also depends on M1 and M2, that is the target and projectile masses. Yeah, yes, Paul. So next one. And you can see this is the schematic diagram from where you can imagine that how thickness determination can be possible. Of course, I'm talking about monoelemental. If it is a compound material, a thin film of a compound material, then you have to do the same formality for both the constituent elements. Okay, and it has an additive effect. So simplistically, to tackle with a monoelemental target, a thin film, you can see the inward path length will be designated as, if this is the film slab thickness or film thickness x, and this is the incident angle here. It makes the incident ion is if it makes theta 1, and the outgoing angle is going to be theta 2, is considered to be theta 2. Then the inward path length will be x by cos theta 1, which you can obtain by integrating over the inverse energy loss. Okay, and why E0 to E has been done is just to give you a feel that energy will continuously be decreasing as it penetrates more and more depth inside the material. Likewise, outward path length will also be x by cos theta 2 rather than x by cos theta 1, because this theta 2 is different here. And you see, E0 is the projectile energy to start with. Let us now see the energetics. As it keeps penetrating, there will be a certain depth beyond which it cannot penetrate anymore. Okay, and from that point, it starts coming back. And the ultimate point from where it starts coming back, there the energy becomes E, and the kinematic factor being K, the bounding point from where that is the highest depth up to which the ions are penetrating, and it has started coming back. Okay, so those backscattered particles, in other way around, which you can detect from the highest depth point, from at that point the ion energy will be Ke, assuming the energy is E. Okay, so it reduced from E0 value with which the projectile energy started entering the film, and the end point up to which it is meaningfully able to probe within that material. So at that point, the energy loss will be there throughout this part, that is x by cos theta 1, that is the inward path length. And after that, energy becomes Ke. So K is the kinematic factor. At that point, if energy is E, then it has to be the starting energy at this point. Here, the starting energy was E0. Here, the starting energy is Ke. And it continuously keeps losing energy throughout its outward path, and then gets detected at the detector with a value E1. And that's why here it is integrated from Ke to E1. Again, remember, Ke was the higher energy and E1 is the relatively lower energy, because during its outward path, which had again the projectile, the scattered particles, that means the helium ions, they again have lost some energy. Okay, and as a result, we can find out the energetics. When physically one can calculate, and likewise, S is the energy loss factor, and from all these values we can find out rather determine the X value. Okay, because here you can see that KE0 is the energy with which it starts going in, and but that is because sorry, KE0 is the energy of the scattered particles which come back right from the surface atoms. Okay, and the energy which is detected for the backscattered helium atoms which come back as the marker moves from the deepest point is E1. So KE0 minus E1, this is the energy, total energy lost over the path while going in and coming back. And that is the total energy loss, okay? And this is designated as the energy loss factor multiplied by the total depth of the sample or the film thickness, for instance, for a thin film. So one can exactly calculate by measuring these energy loss values and knowing the kinematic factor. This is all I showed you in the previous slide how to calculate the kinematic factor, etc., etc. Next slide, please. And you see, if we have two elements, as I was telling you, one element can be designated having a kinematic factor of Ka, another one would be having kinematic factor of Kb. These are unique values. They cannot be same for two different target projectile combination, not at all, because they're mass dependent. And then what we see is step by step, if we do the same calculation, and if the thickness values are Ta and Tb, mass of these elements are present in the target are A and B, capital A and B, as is being shown through the marker. If E0 is the projectile energy and small mp, or mp is the projectile mass respectively, sorry, and then if B, I, and A stand for the back, interface, and surface respectively, and theta is the scattering angle, back scattering angle. If E1 then is the energy at the interface, okay, E2 is the scattered energy from interface A atoms, E3 is the scattered energy from interface B atoms, and E5 is the energy from the back surface, okay, from here when it comes back. And colors are also being different. E0 is projectile energy. So then we can calculate from each depth that how the energy is getting lost. And in turn, one can find out the thickness values, okay? And in the spectrum, it gets reflected by two different signals, okay? Instead of one signal which should appear from one element. So two different signals correspond to two different elements present in the target. And you can also take a note that if A is heavier than B, then the signal will always be appearing more towards the higher energy side, so for the elemental species A compared to B. On the other hand, had B been heavier than A, then B signal, this B signal corresponds to the peak. Tentatively, you can assume that is the peak. That will be appearing ahead of the signal of A related atoms. Okay. So next slide, please. Now, as I told, I mean, with this fundamental idea, we can share some examples of how one can study various different systems of materials which are obtained from, due to alloy formation, either by using ion bombardment, which is known as ion beam mixing. What happens is if there is a thin film or some nanomaterials deposited on a substrate material, and if energetic ion bombardment takes place, which passes through the film inside the target material, basically the substrate, then under ion bombardment, there could be the formation of metastable phases as well as equilibrium phases. Remember, metastable phases are those phases which will typically not be available in equilibrium phase diagram, but they can still form. And silicides and germanides, which are very important contact materials for optoelectronic device industry or semiconductor industry. Many cases, as I told, several ion beam processing steps are utilized for semiconductor industry. These are good contact materials and interconnect materials in large scale integrated circuits, maybe ULSI or VLSI or whatever. And so these are formed during doping procedure, etc., etc. So through one job, two jobs are done. Okay, across the interface, the mixing can take place, and RBAS comes very handy to probe those kind of metastable phase in terms of composition as well as their thickness values. And as I listed here, several such silicides and germanides, they are good for different material where the substrates, for gallium arsenide based material, a good contact material is AuG alloys. Okay, and likewise there are many silicides and germanides which are listed here. We have worked quite a bit on that. I'm not going to those, but just Paul, you can please go to the next slide. I show you one example. Here, gold film was deposited on a germanium thin film, which was further deposited on the silicon substrate. And then these thin films, if you see these, follow these red circles in the RBA spectrum, okay, you see first the gold peak comes, then the certain amount of gap is there on the energy scale. Channel is nothing but the energy equivalent to energy values, because each channel of the multi-channel analyzer can be designated with a certain amount of energy, which is known as channel width. That means within that channel width, within that energy width, whatever number of particles come and get detected in the by the detector, they all will appear within that channel. Likewise, we see that substrate silicon also appears here. Now, the arrow positions actually are indicative of where the original signal should have appeared. That means if silicon arrow is coming here, silicon substrate signal should have started from that place. But you see, it is not happening. It has got pushed towards lower energy value. Likewise, germanium arrow position shows here, points towards here. That means ideally speaking, germanium peak should have appeared here. But you see, it is not happening. This is also pushed a little bit inside. And then let us take the example of gold. Okay, please see that here, gold signal is appearing properly. That means wherever gold signal is supposed to come, it is appearing right there. It has not got pushed towards lower energy side. Now, what is the reason? The reason is, as I told you, heavier mass atoms will appear at higher energy positions because of the kinematic factor. And particularly, second point is the position of their of these atoms, of these species, of the layer from the surface. Now here, gold was deposited on germanium and germanium was deposited on silicon. So had silicon been only the substrate, and would there be no films, then silicon signal will appear with no such gold or germanium signal, and then this red curve would have got extended up to this silicon arrow position, and it would have started. And before that, towards the higher channel positions up to 500, nothing would have been seen. So in that case, silicon would be at the surface. But the moment one deposits the germanium film first on silicon substrate, the equivalent energy that has got lost within the germanium film till the projectile ions could see the silicon atoms, that will get manifested through a shift in backscattered energy in terms of becoming lower energy. Okay, so from this substrate silicon surface, from where the backscattered particles will start coming back, by the time it has lost some energy eventually in the germanium film. So that's why this surface position of germanium gets shifted. Now, why germanium position has also got shifted is the reason is, well, above that, again a film of gold had been deposited. So that amount of energy lost within gold has to be manifested in terms of deciding this position of germanium, because then it is no more the projectile energy. Projectile energy minus some energy lost within the gold film will be the energy with which the helium ions will strike the germanium atoms. So automatically it has to get shifted towards here. higher would be the energy, higher would be the channel number, okay, and the higher would be the backscattering energy values. Now you see red spectrum, that is spectrum drawn in with red symbols. They're the as deposited film. Now this film, when it was irradiated using 120 MeV of gold ions, then you get to see out of scanning electron microscopy, image, that there is no continuous film. The films have got deviated. Okay, this is known as spinodal deviating. They have got deviated, and several bright islands on the black background are created. When we do measurements, RBS measurements from this particular kind of sample, which representative image is right on your screen, with scale bar of this black scale bar is 10 micrometer, we get to see the corresponding RBS spectrum like this. You can see as marked as B. Here again, the signal for gold is intact, but very interestingly, you get to see that germanium has also started appearing at its designated surface position, which is known as surface position. That means had germanium been at the top, from wherever or whichever energy, it should have got backscattered. The helium particle would have got backscattered. Right now, that is happening after ion radiation, but under the as-grown condition, it did not happen. Likewise, interestingly, silicon position has also come back to its surface position. That means as if the projectiles are hitting silicon with the original ion energy with which they were striking the gold atoms. Now, how is it happening? And also interesting thing is the signal of gold atoms has come down drastically. Okay, and then from germanium onwards, you see the spectrum is not sharp. Clearly, a long tail is there, and we can get to see that means a lot of diffusion has taken place. So, what is the reason? The reason is very clear from here. Since swift heavy ions, 120 MeV ions bombarded on the surface of this gold germanium thin film, they first reacted with each other through ion beam mixing. And remember, gold germanium system is an eutectic system. Okay, and here metastable phase formation took place. Gold 0.6, G 0.4. So rather gold 6, G form, you can assume that composition is effectively. And then after these formed, later on, after continuous bombardment as a cumulative effect, the deviating also started taking place due to surface and interface, favorable surface and interface energies being available to these materials. So they get broken into the continuous film, get first react with each other due to ion bombardment, and under continuous ion bombardment, they start forming island. So basically the continuous film breaks like. It is like equivalently a very fertile land under drought condition, when a deep scorching sun with no rain out, actually the entire soil cracks. So like that. So we can assume that the soil, this cracked soil, as if they are islands, and these are the deviated islands. And these islands individually are of composition AU 0.6, G 0.4. And then what happens, you can imagine, when it was a continuous layer, individually within each layer, almost at the same rate, energy was getting lost as the projectile ion was penetrating deep within. And the signal was looking like this in the RBS spectrum. But now these islands are there. Islands will have a certain height. You assume that single island, as if it's a tent-like thing. Just assume. So it has a height, okay, and it has a base. And you can imagine towards the stretched conditions, towards the sides, okay, endpoints, there will be different thicknesses compared to the peak position of this height. So RBS signal that we see actually get diffused. So this due to this diffusion, there's this long tail here. And then height of the gold signal also comes down. The total amount of gold is not less. You can see the signal of gold in the as-grown film was the red, the peak area was from this channel to this channel. But here you see it is a diffused kind of the peak area. So it has reduced in terms of height, but it has got spreaded over the channel. That means several different energies appearing through these backscattered helium particles from gold atoms are getting manifested here. So this is an indication that island formation has taken place, and at the same time, the germanium and gold alloying has taken place, so that these black spots are nothing but silicon. So that's why silicon is appearing at its normal position. That means helium ions are able to see silicon atom directly. They are seeing gold and germanium atoms also directly without traversing any depth. That means that the surface atoms are having all three, gold and germanium in terms of these islands of gold germanite system, and the silicon atoms are appearing through the substrate, because substrate is getting directly exposed, because now the continuous film is transformed into several small islands. Okay, next slide please. Similar example, you see, through TEM studies, I show you here instead of two different bilayer thin films of gold and germanium, here what was done is 1.3 nanometer of effective thickness of gold was deposited on silicon, and then ion bombardment took place. Again, gold and silicon is also a eutectic system, and when this gold silicide island is formed, here gold and silicon both appear at its normal surface positions. And since here nanomaterials were deposited instead of a continuous film, silicon position has not got shifted from its surface position. That means ions, projectile ions, were anyway able to see silicon's target, that is the substrate, right from the beginning, as well as the gold nanoparticles at the same time. So there was no separate loss in energy in the projectile ions to traverse through the gold to reach silicon, or till this could see silicon. Instead, from this TEM image, we can see very clearly these surrounding this island is all silicon atoms. So they will see together gold silicon system as well as silicon substrate. So that is getting manifested. But here, since bigger islands, smaller islands, as I told, their height is different. Here, their height will be maximum. Here, they will be little smaller. Suppose something is penetrated at the edge, here it will be little less. So accordingly, here also the gold signal height reduces, etc., etc. And there was some aqua regia treated treatment was also given. So that blue spectrum where no gold is there, as you know, aqua regia can eat up, can dissolve gold completely. So only the silicon signal was appearing. This was just to show that silicon signal has not changed its position. It was not needed, because no matter whether the gold islands are there or not, right from the beginning, silicon is being seen because they are nanostructured islands. It's not a continuous thing. Next slide, please. Now, this is another example where I will show you that 10 nanometer of chromium was deposited on a thick 300 nanometer thermally grown silicon dioxide film on a silicon substrate. And you see from the cross-sectional TEM image that chromium is a continuous thin film. Okay, we'll see in the next slide that how it gets manifested in the RB spectrum. And it's a polycrystalline thin film. However, under ion bombardment in the form of 38 mega electron volt of iodine ions with charge state of 7+, to the fluence of 5 into 10 to the power 14 ions per square centimeter, the same continuous thin films of chromium gets deviated like we saw in the last slide. And they form several nanostructured islands. However, chromium, when it gets deviated and forms small metallic islands, it immediately catches oxygen atom from the ambience. And so it becomes oxidized. And at the same time, it becomes amorphous. This chromium oxide is amorphous, unlike this chromium continuous thin film. Okay. And as the ion bombardment continues under double the fluence of 1 into 10 to the power 15 ions per square centimeter, remember everything was done in at room temperature. These chromium ions, okay, sorry, chromium atoms with oxide, of course, now the chromium oxygen entities, these nanostructures, they start getting borrowed. What is borrowing? They get as if hammered and start getting inside the silicon dioxide layer. Remember, this experiment was designed to undertake such borrowing kind of experiment because it is Newtonian viscous flow that enables or that helps to tune the surface and interface energy of these nanostructures within these highly viscous under ion bombardment, this SiO2 thin film. So that's the reason they can continuously get hammered and get pushed within the layer. So you can imagine the power of ion beams. It was a continuous layer first. After a certain threshold fluence, this continuous film gets deweighted, breaks into small nanostructured islands. Chromium islands immediately catches hold of some the oxygen, get bonded with that, and forms from originally polydicrystalline chromium layer to amorphous chromium oxide islands. And these islands, under further ion bombardment continuously, they get borrowed into the silicon dioxide layer right below. Not only that, another important aspect here is the shape change. You see this good bit of spherical islands, they get transformed into almost elliptical or nanowire-like shapes as they are going inside. It is very clear from here. They are almost like small nails. You can see clearly they are vertical objects. Okay, the aspect ratio is changed, and this is known as shape changing, shape transformation. Okay, shaping, ion beam induced shaping. Okay, and now next slide please. These are the effects. If we study by RBS, you can see very clearly the virgin, that means the as-grown film, like we have seen earlier for gold and germanium. We get to see that, chromium, this is a signal for chromium, okay, the red one. And this is the signal for SiO2. And this tape indicates actually 300 nanometer SiO2, its width. Originally, this would have come down here, but the substrate is silicon. So as a result, what happens is, silicon being lighter than SiO2, it overrides the SiO2 signal. So for the RBS spectrum is concerned, and everything is very clear from here. And the little bit of shift, I have not marked here the position, but depending on the 10 nanometer thickness of chromium, little bit of shift is observed in the silicon position. Because, and then what happens? You see that shift was nominal. So follow the red plot, red spectrum signal, in contrast with the blue, green, and the magenta signals. Okay, there's a little shift towards the lower channel number. Red is pushed a little bit towards the lower channel number. That is because this is the as-grown sample, and chromium was there at the top. 10 nanometer of chromium was there at the top of SiO2. That is getting manifested. But the moment ion beam induced deweighting took place, as I told earlier, that you see now in between, that means through these islands on the TEM image, if you recall, it is very clear that ion beam can see the silicon dioxide underneath film, also simultaneously with the chromium material. Okay, and so that's why the signal also here comes down. Okay, and as the fluence increases, we can see that is when the borrowing takes place. Signal of chromium is observed up to a deeper thickness, okay, or up to a larger depth. That is because, can you please go back very quickly to the last slide? Yeah, see here, this is the 514 case. That is the blue one. Here, chromium was right there in the form of bonded with oxygen right at the surface. They were sitting on the surface like this. But here, see, this chromium oxide, after undergoing ion beam induced shaping, they are now possible to be seen up to this depth within almost crossing, some are crossing all the way up to 200 nanometer, because the original thickness of SiO2 is 300 nanometer. So now go back to the RBS spectrum, please. And this is what is getting manifested. You see, as more fluence is being put, we get to see higher and higher fluence, of course, up to a certain level, that they're possible, the chromium atoms are possible to be seen up to deep within the SiO2 substrate, underneath film. And that is the reason here the total area is conserved. So peak under the area under the peak is conserved. So Originally, the peak area was very sharp. Sorry, peak was very sharp. Here, peak is no more sharp, but it is distributed over a certain higher depth. Okay, here it was only at the surface. Here it is getting distributed up to deep within the depth of SiO2. Next slide, please. So this is the example, and the shape change of this peak is also because of shaping and burrowing together. Now, there's a special case of ion channeling, as I told you, that this helps us to address problems related to epitaxial thin films or single crystalline materials, and several important aspects as listed here can be studied. Next slide, please. So, sorry, this is the schematic diagram of ion channeling, the conceptual diagram. Here, what happens is, when you talk about random direction, that means all the examples that we saw, I showed earlier, there the beam was falling randomly. Well, there is a direction 90-degree, true, but in terms of crystallographic orientation of the substrate material, it is random, unless and until you align the crystal with respect to the ion beam. And that is the job of ion channeling experiment. So channeling means one has to align the crystal, a single crystalline material, and say its axis or the planes with respect to the ion beam. So ion beam, incident ion beam, has to get channelized through these open vacant positions of the atomic strings. Then it is known as ion channeling. That means the ions are channeled through proper alignment of crystal, physical alignment. So the crystal has to be aligned with a very minute stage, you can assume. We then talk about 0.01 degree or less than that accuracy. So it reaches a very high degree of manipulator, and with several degrees of freedom in terms of rotation. One is known as tilt. The crystal can be rotated with respect to the incident ion direction, okay? And one is continuous azimuthal rotation, and other is with respect to the sample normal, okay? So three possible directions, and then it is possible to be channeled, the ions can be channelized or channeled through these axes, through the axis of the crystal. And in the ideal condition, you can see when automatically when the crystal axis, along the axis, the ions will go through, it will pass through always that through the atomic planes in between the strings of atoms. So where are the scattering centers? They will be drastically reduced. So that will get manifested through this schematic diagram. When any orientation the beam falls on this target, the same target, we get to see such a normal random spectrum, okay? But the moment we align the crystal, that is a manual job. That's the beauty of that experiment. Then the scattering yield, that means backscattering yield, drastically reduces. It has to be, as I told, because when it is getting aligned through the atomic strings in between the vacant spaces, so it's a few angstrom, then of course you can imagine there are very less number of scattering centers, with which the incident projectile atoms will get backscattered from. If they are not there, so they are getting backscattered from deep within where it is no more channel. Next slide, please. Now the question, this is like this. You can thematically think of that when an energetic ion beam is steered into open spaces, that is the channels you can call, between these close packed rows or planes of atoms in a single crystal, that can be called as channeling. Okay. And the steering is the result of a correlated series of small angle collision. You can imagine the ions actually from the surface atoms, you see they form like a cone. It's known as shadow cone. The surface atoms create a shadow cone. Can you please go back to the previous slide? And this is the reason you always get to see a small surface peak for high quality crystal also when you have completely aligned the ion beam with respect to its axial direction. This is the peak, which is known as surface peak in the magenta spectrum. And this arises practically because of the surface atoms. You can go back to the next one. Which sit at the surface and they create a shadow cone for the next set of atoms, okay? And as a whole, what happens is the ions actually oscillates like this, and due to a series of small angle collisions, okay? And these appear due to the high degree of properly aligned atomic positions in the lattice, okay? Next slide, please. So you can skip these things. These are certain assumptions under which this happens. Okay. Now this is one example where I will show you that here biological thin film, which is amorphous in nature, was deposited on a silicon substrate. Okay, and when you do normally without any alignment, anything, anyway, the film was amorphous, so nothing can be done. No amorphous film or no polycrystalline film can be studied by employing RBS channeling, because there is no directionality of the ion beam in that case, because the atoms are all randomly organized. Okay, and in a random for a random RBS spectrum shown here, what happens is uh, there is no reduction in scattering yield. But the moment we are able to channel the ion beam through the substrate silicon, remember the top film cannot be channeled. I mean, within that channeling cannot be achieved because it's amorphous in nature. But underneath substrate is single crystalline material, and that was silicon 100p type material. So within the silicon substrate material, when we are able to channel, use its atomic strings, and in between that, when we are able to make the ion channels, then what happens is scattering centers from silicon get drastically reduced. And you can see 4 to 5 times reduction in terms of the count, scattering yield. So as a whole, what happens is the signals appearing from the constituent element of the film in terms of carbon, oxygen, phosphorus, etc., which were rather very, very poor, automatically start getting prominent. You can see very clearly here the phosphorus peak, oxygen peak, and carbon peak. And remember, RBS is not the best technique to probe these with high accuracy. But on the other hand, if we can wisely use the channeling technique to channel the ions within the substrate and reduce its signal, the reduce the backscattering counts, okay, arising from those substrate atoms, then what happens is the film material, the film constituent elements automatically start giving rise to prominent signals, okay? And as a result, everything happens because lighter mass signals actually override on the higher mass substrate signals. So that's the reason it comes within the background. When you do this background subtraction shown here, you get to see exact amount of carbon, oxygen, and phosphorus can be possible to be extracted. Okay, so that's the kind of good example how we can maximize the use of RBS in terms of wisely using it where the substrate has been channeled. Now, yeah, next slide is okay. Now, this is another example where we are actually studying. This is a byproduct that I'm showing here. This is ion implanted TIU to thin films, where we see that under continuous ion bombardment with 60 kV gold ions, a continuous reduction in the resistivity of the thin films take place. And at the same time, let us see how this gets manifested. Well, that is because due to ion sputtering, a lot of oxygen gets lost and the film starts becoming more and more metallic in nature. So it becomes TiO2 becomes TiOX, X definitely becomes much less than 2. So that's why the resistivity decreases. And this is manifested very clearly here. You see, the lower plot, that lower spectrum corresponds to the Asgron sample. The black one is an experimental, red one is simulated. So here there is no gold signal, not expected also. Okay. So what happens here is we get to see only titanium peak, silicon on which it is deposited, shifted from its normal position, and you see this is the oxygen signal. Okay, the hump is corresponding to oxygen. Now, as gold ion fluence keeps increasing, gold signal starts appearing. Titanium thickness very clearly starts reducing because the width of the signal reduces. And you see, titanium signal is not, position is more or less fixed because it is appearing at the surface. Now, gold is also appearing at the surface because that means gold is reacting with titanium, bonding, forming some bonds, and it is remaining mostly near to the surface. And there is a clear shift. I don't say the titanium peak position does not shift, little bit shifts towards the surface because it is reducing thickness. And silicon on the other end is clearly getting shifted towards the higher energy side. That is because due to sputtering, titanium dioxide film thickness is reducing. And so projectiles are losing actually lesser amount of energy for the samples with higher fluences, okay, with which gold is implanted. So that means gold implanted samples with highest fluence. In that case, reduction in titanium dioxide thickness is highest. So silicon atoms could be possible to be seen by the projectile helium ions much earlier compared to the as deposited pins, but the signal of titanium was pretty thick. And gold signal also keeps on increasing, clearly understandable because it's higher and higher gold plane. So gold is reduced, retained mostly near to the surface, and that gets manifested, as I told you, that the sample becomes more and more metallic in nature. Next slide, please. Well, this is another schematic of how you can analyze. Had it been a single crystalline material, if you do an implantation, near surface region may be highly damaged or amorphous, and you can find out the depth of amorphous layer or the degree of damage from such simple calculation. A is the area of the peak, okay, and this is after channeling condition being achieved. See, original material under random orientation, that means when we have not done any alignment of the crystal with respect to the incident ion beam, this is the signal. Now, when it is completely channelized, the ions are channelized through the axial direction, then the backscattering signal is supposed to come down so drastically corresponding to the virgin, okay? And you get to see here the small surface peak as I indicated earlier. Now, the same sample, if undergoes ion implantation and then channelized, then you get to see that this surface peak becomes more prominent and is spreaded up to a certain depth, which is the depth of amorphization or disorderedness. And then you see automatically it is difficult now to match in terms of reduction in silicon signal so much of the substrate signal because it goes up, it is expected. And then if it is completely misoriented with respect to the incident ion beam, or it is absolutely amorphous throughout the sample, then it has no other way, it will match with the random signal. So from here, you can easily calculate the number of displaced atoms per square centimeter, that means the degree of damage, etc., from this kind of ion channeling technique. Next slide, please. And you can also find out this employing this technique, solute atom positions, location of solute atoms, whether it is self-interstitial or the impurities are sitting in interstitial or substitutional positions or little displaced, etc., etc., depending on the signal that appears during the channeling measurements. You can decide exactly where the atoms are located. Okay, next slide, please. So it's a very, very powerful tool. That's what I am schematically showing this. The many aspects. You can also decide, address these locations, etc., etc., when it is present, and automatically this shows the tremendous power of RBS channeling technique, that how even an amorphous material, when it starts getting recrystallized, can be directly addressed. Next slide, please, by utilizing this technique. Now, the next example is actually ion beam induced epitaxial crystallization. Okay, what happens is the random corresponds to the sample, okay, with which we started with the silicon sample. Virgin is example we have just now seen, the red circles. So before doing any treatment, this happened. When we amorphize the sample, you can see the signal came down drastically with the stipulated width, as we saw through the schematic in the last slide. Okay, this magenta squared signal is obtained from an as amorphized, as I told. If up to a certain depth everything is amorphized, for that depth we cannot channel the ions through the substrate signal. So automatically these gets added together with the substrate signal. The substrate signal before amorphization through ion beams came up from here to here, from the red circles to the magenta squares. And then it remains like that as this amorphized sample further undergoes energetic ion bombardment as elevated temperatures. You can get to see that the depth, that the thickness of the amorphized layer starts continuously reducing, and at 350 degrees centigrade, its quality, crystalline quality also improves, because it now improves from the as amorphized sample more than 50%. You see the substrate signal also, it is very near to the experimental point. Some of them are very near to the originally procured sample, that means the commercial sample with which we started. And from here, you can see that depth of amorphosity or disorderedness has come down. If we go a little bit more on the temperature, elevated temperature during the bombardment, we can reduce this further. Okay. Now, this peak corresponds actually to the krypton, which was used to amorphize the sample. Okay, so let us not get into this much, but it is also very clear that with increasing temperature, this also reduces drastically. Okay. Now, so we can find out the activation energy for this method also. And RBS channeling was performed by using 1.6 MeV helium ions. Next slide, please. Now I show you very quickly some importance of some applications of ERDA technique. Mostly it is useful to detect hydrogen and its isotopes, as I told you, simultaneously if they are present. And as you know, hydrogen is absolutely important. Okay. The only difference is hydrogen being so small, it diffuses so fast in any material that we live with this. Take my words, I repeat, we live with the situation. Even in our hands, some moisture will always be there. We don't consider it because we can't count it. It is so small, but still it is there. Okay. Likewise, in any material, the presence of some amount of hydrogen is almost inevitable, unavoidable. And importance is its chemical bonding, diffusion, material strength, etc., etc., etc. Electronic structure, optical properties. So many materials, whatever property we characterize or study, remember they are with the presence of hydrogen. The only way with different treatments, if we see actually that the properties are changing, then it can happen only when hydrogen quantity also with the several processing steps are going down or going up. And hydrogen can get into any material through two possible ways. One is intentional and another is controlled. Okay, intentional and controlled could be one way, and unintentional and uncontrolled could be another one. Intentional and controlled incorporation of hydrogen in any material could be through plasma or ion implantation. And implantation also will be offering another advantage of depth selectivity. And unintentional and uncontrolled could be during crystal growth, sample preparation, cleaning, etc. I'm sure yesterday Professor Rajendra Singh had talked a lot about this semiconductor cleaning, etc., etc. also. So there, during chemical etching, chemical cleaning, etc., also hydrogen can get into, depends on the nature of the material which is under treatment. Okay, next slide, please. However, hydrogen is very difficult to detect. I have told earlier also, and will reiterate again. Now here, different, as I told, helium bombards a target, and hydrogen will get recoil. It cannot, I mean, hydrogen is lighter. Helium cannot get backscatter after scattering from hydrogen. Okay, so hydrogen will also get recoil. At the same time, helium will get backscattered from the target atoms, which are heavier than that. So red atoms, okay, schematically drawn, they are heavier. So helium will get backscattered, of course, from those atoms. But hydrogen, the moment it encounters the helium ion as a projectile, hydrogen gets recoiled towards the forward direction. And then what happens? It's the hydrogen and deuterium or tritium, if they are all present here, along with backscattered scattered helium, they all will be going towards the detector because it's symmetric over the cone it will get. But this helium is undesirable. When we talk about detection of hydrogen, deuterium, tritium, etc., and its hydrogen and its isotopes, the scattered helium is undesirable species. So to get rid of that, one has to use an absorber foil, very thin absorber foil of lighter elements. I mean, it has to be made up of lighter element like mylar foil or aluminum coated mylar foil to make it a little stronger like that. And then the detector comes. But you know, disadvantage of this technique that comes in picture in the form of additional energy loss within this absorber foil. So it's not only that the fact that helium is getting completely scattered, helium particles are getting arrested within this absorber. Hydrogen is also losing some energy. It cannot happen. That we cannot, it will not lose energy. And then it is reaching, only advantage is hydrogen will lose less energy compared to helium or even higher masses, and it will still be reaching energy. But then that means what happens? it becomes limited to depth of penetration that we can gather information about or from. Why? Because hydrogen which are coming recoiled from a deep inside of the material, they will not be able to cross this absorber foil. They will also be getting arrested or absorbed by this absorber foil because they are energetically lesser. Only close to the surface and near surface region. So here hydrogen will reach the detector. So that means this technique is little bit limited in terms of the penetration depth. Okay, and these are the formalism. I mean, from where this is formally. Here also kinematic factor is there, recoil kinematic factor, and here also you can see that how energy value varies. Okay, energy also here varies with 1 by E0 square, and similar formula of recoil yield is there. So one can calculate precisely in a non-destructive way how hydrogen is getting hydrogen is distributed over a depth. Next slide, please. Now I show you a typical ERD spectrum. This is 1.7 MeV helium ions, which actually penetrated within the hydrogen and deuterium implanted aluminum foil, aluminum target. And as I told, they can be probed simultaneously. When 1.7 MeV helium ions actually bombards this aluminum target implanted with hydrogen and deuterium isotopes, you see that deuterium being heavier than hydrogen isotope, where proton, it appears ahead of that, like any other heavy element for RBS signals we have seen, and then hydrogen appears. Okay, next slide, please. Next, please. Okay, now I'll show you also very quickly one last example of DLC films, which actually contain different kind of film, hydrogen amount of hydrogen rather, are due to its growth processes. Okay, one can tune the content of hydrogen in diamond-like carbon films, which are very technologically very important material. So, but due to different processing states, it can contain actually very different amount of hydrogen, and hydrogen can be present from starting from 1 atom percent to 50 atom percent. So those 50 atom percent hydrogen containing films are very floppy in nature. Okay, and less amount of hydrogen actually make these films rather hard, and they can actually become tetrahedral amorphous carbon film like, and they can be something compared to diamond like properties as well. Very high quality films. But remember, hydrogen content actually critically determines the film structure and properties. Lesser is the hydrogen concentration, hardness and band gap increase, and they become more and more diamond like. And mostly bound hydrogen is determined by indirect methods, FTIR or Raman, but as I told, ERD is a very powerful tool which can also address directly to help us quantifying hydrogen in an absolute manner. Okay, next slide, please. Now we show you the real example of DLC film being probed by 1.5 MeV helium ion beam. But this is the hydrogen spectrum. Hydrogen is pretty uniformly distributed in the sample. However, depending on the hydrogen content, it was observed by us that hydrogen evolution can take place under energetic ion bombardment, which is nothing other than the probing helium beam. Okay, so to start with, the hydrogen content was like this, and right at the beginning. So we kept on acquiring the spectrum after very less amount of time window, say every 3 to 5 minutes with very low current. We kept on acquiring these hydrogen spectra. And as a result, we could see that after certain charge collection on the target, corresponding to, which definitely corresponds to certain amount of ion fluence, that is jot down here, it is converted here. You see, hydrogen by carbon ratio is actually keeps reducing. That is because carbon is remaining fixed. So hydrogen concentration actually reduces, and you can see in the beginning, the reduction is almost exponential, and then it slowly shows a saturation. So these are the 5 microcoulomb spectrum, and this is 35 microcoulomb spectrum. So you can clearly see a significant amount of hydrogen loss has taken place. And this happens due to the evolution of hydrogen, it gets lost from the target. Remember, this doesn't happen for every sample. So this is not that it's a destructive technique. This is a nature of ion matter interaction actually promotes some loss of certain amount of hydrogen from the target. I'm skipping due to time restriction, so I did not include. Have you been seeing in case of diamond film, synthetically created CVD diamond film, hydrogen does not get lost. Whatever it is, it remains there. So it depends on how much amount is there and how it is making the bonds, etc., etc. So next slide, please. So any time one does some measurements using RDA, if hydrogen evolution is seen, then one has to address certain fundamental questions. So question is, how much is the original hydrogen content? See, my question is, if I get to see that hydrogen is getting lost up to a certain depth, up to a certain degree, then the question is, who says me that right at the beginning, whatever I measured was absolute, that it was not less? Because right at that moment, hydrogen also did not get evolved. Who assures that? Yes, it's a very valid question. One should have addressed that. So one way is to extrapolate. Since the last curve we have seen, almost kind of exponential decay was there, one can extrapolate and find out where about y-axis hydrogen content value is by C ratio, y touches, that would be probably the original one. However, another test can be done that, if we know a known material with known hydrogen content, that can be used as a standard material. So for instance, KDP, ADP, like potassium dihydrogen phosphate or ammonium dihydrogen phosphate, okay, here, the content of hydrogen is known. It's a stoichiometric compound. It's a crystal, K2PO4. So here, if you can measure initially, so then you know how much hydrogen should be present. And from there, doing the calibration with respect to the standard, you can pretty exactly find out what is what. And so the question is there a destructive? Answer is no. Studied on many wide variety of materials throughout the world since its discovery. And how hydrogen evolution can then be explained. As I told earlier, it's an ion-solid interaction that leads to, which can be explained through phenomenological modeling, as we have done in several systems. I have shown only one example for one type of DL sequence. And so this is the conclusive statement. It's not a destructive technique. Hydrogen evolution has to be taken care of properly. It has to be addressed. It cannot be ignored. As I told you, whatever we say is due to hydrogen, we live with that situation. If we don't measure, and for sure, if you go back to the last slide, please. If we don't measure, definitely these two samples under certain amount of helium ion bombardment before and after, they will show different property. And then we keep thinking, oh, they are different materials. It's not. Due to some hydrogen loss, the material property is getting changed. Next slide, please. So that's the take-home message I would like to send to you. That it is ion-solid interaction. It may give rise to hydrogen evolution depending on its nature of bonding with the host material. If not, then not. It's not mandatory that with any ion bombardment, helium ion bombardment from any material, hydrogen has to evolve. It's not like that. Next slide, please. So it is, once again, as a microstructure dependent hydrogen evolution, particularly for DLC kind of material. Okay, and for different films, it is very different. More compact film, bond breaking probability with hydrogen is higher, but net hydrogen evolution is less, that we have experimentally observed. And compact, high density DLC films, as I told, more diamond-like, with lower hydrogen content. They generally will have less number of traps, which basically arise mostly from sp2 related bonds. So it is higher the sp3 bonds. Okay, it is less likely that hydrogen will evolve. Okay, although they will still be DLC films. Next slide, please. This is I'd like to conclude here that ion beam analysis in the form of RBS is a very efficient tool for composition analysis of novel materials, particularly for the heavy elements, starting from oxygen and beyond up to uranium. And RBS channeling is a special case where in a non-destructive, unique way, one can study crystal defects, degree of damage, or defect engineering can be studied, or ion beam induced epitaxial crystallization out of very And hydrogen evolution leads to the possibility of tuning hydrogen content to obtain different tunable materials properties in chemicals and other materials. And I would like to thank all my collaborators and students and past mentors in these studies, whoever were involved. Many examples I did not show, which were done in collaboration with Professor Santanu Ghosh from IIT Delhi during his PhD studies. And we have done a lot of electronics sputtering studies also from technologically important materials. And at the end of the day, I'd like to thank you for your kind attention for this talk. Thank you very much.
Thank you, Tapoda, for giving
Welcome.
us a very illuminative, innovative, and inspiring talk. And we all have learnt a lot. And if you will permit, there are a few questions that I would like to ask you from our participant.
Please.
So, can you ready? So,
Yeah,
are you ready,
please.
Tapoda? Yeah. So, the first question is, Tapoda, and that question is RBS is also feasible for polymeric material loaded with nanoparticles? So,
Yes.
please.
As I told, like the diamond-like carbon film, we have seen, depending on its bonding, etc. A lot of ion matter interaction based studies have been made on polymeric materials. And if metal nanocomposites are also there based on polymeric materials, many interesting features evolve after compartment. So in principle, there is no restriction. Only the lighter elements may get lost or may get evolved during characterization a little bit, but and this technique has no restriction to study.
Okay,
Absolutely.
thank you. The next question is related to, basically it is from Bhartid, and she is asking that can we use thermoluminescence to ion beam dosimetry for alpha or beta radiation? How? Explain in short.
I'm not an expert of thermoluminescence or dosimetry, but RBS, whatever RBS can come in materials. Okay, it is basically composition and analysis or thickness study, etc., etc. But if that has any bearing to understand the thermoluminescence process, probably one can think of how to correlate that.
Okay. Thank you, Taputar. The last question one is from Surendra Singh, and he is asking that please mention if study of ion beam radiation effect is suitable in nanoferrite like zinc copper ferrite.
What kind of studies you want to do, that depends. Again, if you are talking about studying by RBS, you can always study, but then you have to see that if the neighboring elements, constituent elements are having very close Z values, then you may not be able to separate them very nicely. For instance, if you are talking about nickel ferrite or so, nickel and iron may not be possible to be separated properly by RBS studies. Okay, but so for other ion beam modification related studies, anything can be done, no problem.
Okay, so that's all.
You want to know, if you talk about the thickness measurement, yes, but only difficulty will be if you are using a nickel ferrite, it may overlap, but zinc ferrite, it may just survive, depends on how thick they are, etc.
So thank you, Tapoda,
You're welcome.
and nice to see you here. And now I would like to move to the Dr. Jaspal. Jaspal ji, it's your
Yes,
time.
sir.
Now
Yes,
you
sir.
can start. Okay,
Yes.
thank you.
Yep.
Yeah.
Sir, Som sir.
Yes, please.
Yeah, can I continue with some more questions?
Yes, please, please.
Yeah, yep. So, so you have shown some simulated curves. So I would like to know for my participants, what are how these simulation curves are obtained?
The simulation studies, mostly simulated curves are obtained from standard commercially available programs. There are several programs available in the market. One is known as RAM, another is SEAM NRA, and another is Data Furnace, and there is another one known as IBADT, and like that. Okay?
Yes, sir. Okay, so then there is a question. Yeah. Okay, so why to do channeling? It's from Ankit Kargeti. He's asking why to do channeling. You have already answered it in your talk, but if you would like to.
Yes. Once again, it's good that you asked. I mean, when you have a single crystalline material, or say for instance, if you have an epitaxial thin film, or if you have an amorphous material deposited, thin amorphous material deposited on a substrate to enhance its resolution in terms of detection resolution, okay? Or you want to study the degree of damage or disorder created due to some processing technique in the near surface region of a material. Ion channeling using Rutherford backscattering spectrometry is the only answer to precisely quantify it in a non-destructive manner. So that's why we could do channeling. Okay. Apart from routine composition and analysis, also is possible during that channeling.
Okay. Okay. Thank you, sir. So is it possible to do RBS on powdered samples too? And what are the precautions that should be taken? That should one take?
Well, it is if you are really meaning powder samples. I mean, if this is a spreaded kind of particle, then you will get to see the support material as well. But so it is not desirable. So the best choice to make it is a little bit harden it in terms of making a pellet or like that.
Okay. Okay.
And whatever beam spot, that is typically you can go down to 2 millimeter, 3 millimeter, anything. The sample size can be little more than that. Even you make a small pellet of that 5 millimeter diameter, still it is more than enough. But it's always desirable, because otherwise the material on which you are spreading the powder, that may come in picture and you actually will never know from where this is coming.
Okay, sir. So there is one more question. We get to see channel number on x-axis of a RBS spectrum, and then sometimes it is energy. Okay, energy of the helium alpha particles. So how is this channel number converted into energy of alpha particles?
We get to see, actually, as I told, this is nothing but energy only of the backscatter energy of the alpha particles.
Right.
Now, what happens is, to set this fact that how much each channel has a width in terms of energy. That means, what is the channel width? That means in terms of keV per channel allocated to each channel number. One has to actually study two standard samples right in the beginning, which I did not tell.
Right.
Now, the best way to do is some material to deposit. There are two ways. Basically, two elemental signals need to be obtained without any impurity intervention. So, for instance, silicon is not a best choice to study because there is always the presence of a native oxide. So, two standard materials. Say, for instance, gold is a very popular choice because gold will not get oxidized if it is thin gold film is deposited on silicon. Okay, and then you take another such precious material, say the platinum or like that, which will not get so easily oxidized. That is one possibility. And then study the backscattered energy value from individually from these two standard target material, and then you plot the backscattered energy versus which channel position the gold signal appeared in the spectrum or the platinum signal appeared in the spectrum. Okay, and you plot so channel number versus backscattered energy, and you will get to see a straight line with an intercept will be appearing, and this intercept will be giving you the zero channel energy, and from the slope you can find out keV per channel. So that's the channel width. So each channel will be corresponding to that much energy. Now these days there are smarter ways to handle this problem to avoid wasting time or avoid using precious materials. What can be done or is done is to make use of silicides or germanides, where suppose you are using a tungsten silicide on any substrate, for instance on aluminum itself, doesn't matter. Now tungsten silicide is a composite, it's a compound formation has taken place. So both tungsten and silicon, as we have seen for gold germanium example, as we have seen for gold silicon example, both these materials will be appearing together in the RBS spectrum. Okay, so that is the advantage. So two signals which are distinctly different in terms of mass, the Z values, they will be well separated from the RBS spectrum. So you know that in that case the advantage is the projectile ions are hitting both types of atomic species present in this top layer, which is a compound layer, at the same time. So nothing is energy shifted towards lower energy or higher energy side. So from these two signals, again you plot that curve, draw that plot where backscattered the channel position. That means wherever the peak position is appearing, corresponding to that channel position. If you draw a projection on the channel axis, x-axis, you get the channel position where it is appearing, the signal, and its corresponding backscattered energy. That is very easy to calculate Ke0 value. You know the kinematic factor, you can easily find out from book itself, any standard book, or you can calculate using that preliminary formula. It's a simple arithmetical formula. You plug into all those values, projectile mass, etc., and you find out the scattering angle. So kinematic factor multiplied by the incident projectile energy will be the backscattered energy for a particular species. Now I told two different atomic species will give you Ka-E0 and Kb-E0. Again, you get 2 points, and you plot that. Again, you will find a straight line that will have an intercept. That intercept value on the y-axis will provide you the zero channel energy, and the slope of that curve K will appear in terms of Keb per channel, because x-axis we are plotting channel, y-axis is the backscattered energy corresponding to that channel where the signal appeared. So from that you can find out what is the channel width. That means each channel. So that's how I see in many experimental spectrum, in research papers, people do have a tendency to show it also as the upper x-axis, which projects actually the energy. So there you can directly have an idea that corresponding to each channel what is the energy. Okay, but the procedure to find out the channel width, how much energy is associated with each channel, is this.
Okay, thank you, sir. And there is one more question from Ankit Kargeti. He's asking, how do EDS, energy dispersive X-ray analysis, and RVS compare for compositional analysis?
No match, because EDX is an indirect method. Okay, there are lots of ifs and buts, and RVS is a direct method. Okay, and it gives you pretty quantifying EDX spectra is very difficult. Exact quantification is mostly it is better to present them in a relative way, but RVS gives you a direct quantitative estimate of elements present there. No second thought about it.
Right, sir. So I guess that will be all from the question answering side, and I would like to thank you on my behalf as well as on the behalf of our ECTMR organizing committee. So thank you very much, sir, for your wonderful talk and answering so many questions from the participants.
I would be happy if Sandeep has also to ask on behalf of some of their these things.
Okay. Is Sandeep around? I'm not sure if he is disconnected. Most of us face these network issues, so okay, I guess he's not around.
And in a personal note, I must say that it was a good opportunity to see you, both you and Mukesh, after a long time. Take care, and once again, thank you very much for giving me this opportunity to